slideshow mode and just get going here. Okay. So we finished up talking about finding angles and lengths of vectors, and we're just sort of talking about vectors and how to describe them just in the mathematical context, and we're very quickly going to go on and use them to describe velocity and acceleration, and then get back to physics in 2 dimensions and 3 dimensions. What does Giancoli mean? This is a reading response question. What does Giancoli mean by vectors can be translated parallel to themselves? I don't understand what translation means in this context. And how can that be useful in adding 2 vectors together? The translation, we'll talk about adding vectors in just a second, but translation parallel to themselves means that you can always take a vector and move it. I guess I'm having trouble since I'm not in slideshow mode. You can move it so that you don't change the magnitude and you don't change the direction. So you just move it without changing its direction at all and its magnitude. And we consider that the same vector. So you know, earlier on we said, well, you can draw vectors as arrows, or you could give their components, or you could give the length and the angle. But they're not really completely equivalent because there's many vectors that represent the same vector. Many arrows that represent the same vector. And that's because a vector, by definition, only has a magnitude and direction. And notice all those different arrows have the same magnitude and direction. So when we draw an arrow in the plane somewhere, and it represents a vector, like a velocity or a force, we're free to just willy-nilly move it around the plane as long as we don't change the magnitude and direction. And you'll see we do that all the time, including in addition, subtraction, multiplication, scalar multiplication. So, and I'm still going a little bit quickly through this because of the stuff you watched the videos on, I think on Monday, the end of that material. You learned how to add vectors, both when the vectors are represented as components, you just add the respective components to get the x and y components of the sum vector. And you learned about the head to tail and parallelogram addition methods, and I'm not really going to say more about those. A lot of people have a question of, when is it appropriate to use each different method for adding vectors? I think that means the tail to tip or head to tail, whichever one you call it, and the parallelogram method. And you can always use either one, but it's sort of more convenient to use the parallelogram method if your 2 vectors have their tails already joined. If they happen to be drawn that way, I wouldn't want to do tail to tip because I'd have to move one, and that's just more work. So if they're drawn like this, use parallelogram method. It looks like there's more drawing, but at least I don't have to move the vector. And if they're drawn with one's tip at the other one's tail, use the tip to tail or head to tail method. So there's no superiority, it's just convenience. They're both completely equivalent, it's just a matter of convenience. Subtracting vectors, same kind of definition to get if I have a vector r and a vector s and they have components, rx and ry, sx and xy, to get the x and y components of the vector, which is denoted by r minus x, you get the x component by subtracting the respective x components of the 2 vectors. Easy enough. It's the only definition you really could make up that would make any sense. Now, for the pictorial way of adding vectors, someone gives you a picture of an arrow and another picture of an arrow. Here's r and s, and we want to subtract them. There are, again, 2 different ways you might do it. One is that, if I want to take 3 minus 1, I can think of that as 3 plus -1, right? And for us, we'll find out that the negative of a vector is just the same vector that points in the opposite direction. So in this case, one way to subtract vectors is to say, oh, I've got a picture of r and a picture of s. I'm going to use the head to tail method, except that what I want to do in r minus s is add r to the negative of s. And the negative of s is just the same as the vector s, but pointing the exact opposite direction. And so you align them tip to tail, move them around however you have to. It's a drawing exercise, so you're not going to get anything super precise. But here's r. I've just moved it over here. Here's s, and I've drawn it in the opposite direction. So minus s is going down and a bit to the left. And then I go from the original tip to the final tail. That's r minus s. Just added r to the negative of s. Similarly, if their tails are joined like this, then r minus s is drawn from the tip of one of the vectors to the tip of the other vector. And you have to know which way to go. So one way to remember it is just to say, when you write down r minus s, you always end up on the tip of the one that comes first. So r minus s points from s to r over there. And s minus r would point in the opposite direction, right? It would end up on s. It would end up on the first one in that case. And again, why would I prefer one over the other? It just depends on how they're drawn in a particular problem. One may be just directly easier than the other. Okay. Is it true when you subtract vectors? Someone asks on the website that the order does not matter. No, the order does matter. R minus S and S minus R, one points from one tip to the other tip, and the other one points from the other tip to the one tip. So they're negatives of each other. They point in exact opposite directions. Why do we care about subtracting vectors? This is going to be very important for us in just a second. You know, if I say, here I was at time t0, I'm going to say, where was I relative to the origin at time t0? Let's draw a vector to where I was. So here's a little ant standing there. The ant walks at later sometime t1. The ant is passing this location. There's where the ant is at time t1. We want the displacement to be the final position minus the initial position, just like it was in one dimension, right? Displacement was x final minus x initial. Here it's the final vector pointing from the origin minus the initial vector pointing from the origin. That's a difference. And so it will find the same thing for velocity. Where, you know, if you align the vector's tails, you're just going to point from one tip to the other tip. The third operation you learned about was scalar multiplication of a vector. And that's to say, if I have a vector and I have its xy components, I can form a new vector, which is 3.5 times that vector r. And its components, of course, are 3.5 times the original components. And the vector, sorry, the arrow picture is even easier, or easier than the other cases. Not much of a construction. Here's a picture of r. I can move r over there without any consequence, draw it anywhere in the page you want. A picture of 3r is just 3 times as long. So it's called scalar multiplication because it rescales the length of the vector. Doesn't change the direction, but it rescales how long it is. So there's a picture, roughly speaking, of what 3r would look like. Minus r just switches the direction exactly opposite. Minus 2.5r should be in the opposite direction of r and 2.5 times as long. Okay. Why would we multiply a vector by a scalar, someone asks? Well, you know, for example, if I said, here's a vector that represents me pushing on the corner of this with a 1 pound force. In that direction, it has a certain length in pounds. What would be the vector that represents me pushing in the same direction with a force of 3 pounds? Well, it would be in the same direction and 3 times as long. So nothing world shattering there. Okay. When we have these operations, we can build combinations of vectors into new vectors. Now, we won't do too much of this, but if I, you know, earlier on, I guess this was in Wednesday, we found out the components of this vector A and this vector B. A had components -3 and -2 for its x and y components because in going from tail to tip, I go -3 in the x direction and -2 in the y direction. So there are the components of A and B. And for some reason, I want to get the components of this capital B, which is a minus 2 times little b vectors. Well, I would just start building it out of components. The components of -2b are just -2 times the components of b. I've done that right there. And then I can just add a to -2b to get the result. And the components end up being -5, 2. That means starting at the tail, I go to the left by 5 and then up by 2 to get a picture of what that vector is. All right, so that's addition, subtraction, scalar multiplication. We're going to be using those a lot. All right, so finally into the stuff that you didn't watch the videos on Monday about. Let's talk, I guess maybe I should stop and say, any questions on the generic vector information and trigonometry stuff we've been doing? We're heading back into physics now.
Can you hear me, Dr. Kelly?
Yeah, is that Grant?
Yeah. You said something that I just wanted to make sure I heard you correct. You said that you can change the vectors like direction and like momentum without it being a new vector. Is that correct?
What I said was, if you have a vector, you're free to move it around as long as you don't change the magnitude or direction.
Okay. That
So
makes
if I have a vector, this is say I'm going in that direction at speed 3 meters per second. Why'd you draw there, you might ask? Well, I don't know. I just picked that spot on the board. If I said, no, this is my velocity vector, there's no sense in arguing which one's correct. I'm trying to draw the same vector as close as I could draw it on here. There's no sense in arguing which one's the correct vector. A vector only has a length and a direction. These both have the same length and same direction. There's no sense to where a tails of a vector is located in space. We can draw it wherever we want. So if something's moving at 3 meters per second, when we draw its velocity vector, we don't really care where we draw it. What matters is the length and direction. Good. Okay, let's go back here. I'm still wondering if I can get to slideshow mode. No, it's not going to let me. I'm not sure what's going on here. Why I can't get to that slideshow. What is going on there? Can't use my digital pointer when I'm doing this, so I have to point with the mouse, unfortunately. Okay, so let's use those ideas of vectors now to generalize our formulas for velocity and acceleration to 2-dimensional and 3-dimensional kinds of ideas. So here is an object, and it's supposed to be an ant walking around in the XY plane. It's following this path that's kind of shown in blue there. And at time t1, some earlier time, it happened to be passing by this dot here. At time t2, it's passing by this other dot over here. And notice it didn't go directly between them, but it wiggled around out of the way and then happened to pass that. We want to define the average velocity vector, not because anybody cares about the average velocity, but it's a stepping stone to the instantaneous velocity, which is really what we want to get at. And remember our definition from one-dimensional motion, the average velocity was just the displacement divided by the time that elapsed. Okay, so the displacement we agreed is if the object is here at the earlier time and here at the later time, we're just going to draw the displacement as a vector pointing from where you started to where you end up. That kind of makes sense. That's what we would expect the displacement to be. You went that way, right? We often write the displacement as a difference in two vectors. And here I haven't shown those two vectors, but if I put them in for a second, here R1 represents where relative to the origin it was at time t1. R2 represents where it was relative to the origin at time t2. And notice that the displacement vector is the difference of those two vectors. In other words, these two vectors have their tails at the same location, and it's pointing from one tip to the other tip. So it really is a difference of two vectors, but I'm not going to draw those vectors in because it kind of clutters the diagram. So let's leave them out here. So it's R2 minus R1 over delta t is the average velocity vector. Oh, yeah, I forgot about my symbol's not showing up here. This is supposed to be a little arrow over the top, not a V. So this is V with a little arrow over the top, and this is a R with a little arrow over the top there. Sorry about that. Didn't translate from my computer well. The velocity is supposed to be the displacement divided by the time, where we let the time get smaller and smaller and smaller. So my instantaneous velocity as I'm moving along a path is calculate my displacements for a small amount of time and then divide by the amount of time. The displacement's a vector, so it's going to tell me which way I'm going. Let's do that for the ant here. Here's a much later time. I'm going to consider an earlier time that's closer to t1 and an earlier time, and I'm drawing the displacement vector there, right? Now I'm getting pretty close, and I might say, let's approximate my instantaneous velocity by the average velocity over this short period of time. Here's what delta R looks like. And we're told we want to calculate delta R over delta T. Delta R is shown as that green vector. And notice that when we have that delta T in the denominator, we can sort of factor it out. This delta R in the last expression there is the displacement. And we're kind of just multiplying by a number out in front. This isn't a vector. So what we're doing here is multiplying delta R, scalar multiplying it by 1 over delta T. And that's just going to change the length. It'll also change the units because delta T has units. But remember, when you scalar multiply something, you don't change its direction. You just change its length. So that means if I go for a very short period of time and my displacement is given by delta r, then delta r divided by delta e is just delta t is just a rescaling of delta r. And what that means is my instantaneous velocity at time t1 is going to point, well, it looks like it's kind of tangent to the curve that I'm walking on, or that this ant is walking on, right? Delta r looks like this, and we're saying the instantaneous velocity is just delta r over a very small period of time, scalar multiplied by something. And if delta t is small, it's going to make it long because delta t is small. So it's still going to have the same direction. It's just going to be rescaled. So the instantaneous velocity you can see from this is always tangent to the curve at the point that the object is at. So at this particular location, time t1, if I draw a vector that's tangent to the curve along the direction that time is increasing, so I draw the arrowhead along the direction that it's heading at that instant, that would be its instantaneous velocity at time t1 maybe. At time, if t1 were over here, I would draw another vector that's tangent to the curve. I don't know about the length. I'm just kind of making up the length. And there's another, if t1 were over here, the velocity vector is tangent to the curve. Okay, that's the velocity. The speed, which means how fast am I going, or how fast is this ant going? That is just the length of the velocity vector. Okay, speed is the length of the velocity vector. And you can see if I draw the velocity vector in the xy plane here, to get the length of it, I could use the Pythagorean theorem, right? This is the meaning of the x component. This is the meaning of the y component. The length of this vector is just going to be the square root of vx squared plus vy squared. So it's a little bit more complicated than it was in one dimension, right? In one dimension, we just said, oh, if you have vx, the speed is just throw away any minus signs that you have. But here I got to be a little bit more creative. I have to use the Pythagorean theorem. Yes? Magnitude and length mean exactly the same thing in the context of vectors. So yes, you could say the magnitude or the length. That's what we mean. Okay, on to acceleration, because as position is to velocity, or displacement is to velocity, velocity is to acceleration. So let's look at the definition of acceleration. It's just going to be a repeat here. Again, here's my ant walking in the xy plane, and I'm going to imagine at time t1, let's pretend this is its velocity vector. It's at least tangent to the curve. And at time t2, here's a later velocity vector, t2, as it was passing by that point. They're both tangent to the curve because they're velocity vectors. And to calculate the average acceleration, just like average velocity was delta x, or the change in r over the change in t, displacement divided by time, acceleration is the change in velocity over the change in time. And to calculate the change in velocity is just the final minus the initial velocity, or v2 minus v1 here. In order to do that, I probably want to put the tails at the same location, because if I want a picture of what delta v looks like, v2 minus v1, one of the ways we know how to subtract vectors is when their tails are at the same location. So I've redrawn those two vectors without changing their length and without changing their directions over here in green. And then if I want v2 minus v1, that's what delta v means, that goes from the v1 tip to the v2 tip. It ends up at the one that's the first one in the subtraction, right? But who cares? Because we're not after average acceleration. What I'm after is, what is the acceleration when the ant is passing t1, right? Or some other time. How do I envision that? And all I have to do, same thing as we did before, to get the instantaneous acceleration vector, I have to let those times get closer and closer and closer together, and then take the subtraction between those two and divide by delta t, or scalar multiply by 1 over delta t. That's a little bit hard to visualize, but you might imagine something like this. If something is rounding a curve, maybe there's a car going around a curve like this. And at one instant in time, it's going with a velocity vector that looks like this. And of course, it's turning, so its later velocity vector looks like this. Which way is it accelerating? Well, these were pretty close times, so I'm just going to do delta v over delta t. delta V looks, I might call this V1 vector, and here's V2 vector. If I want to draw V2 minus V1, what I'm going to do is try to draw those two vectors down here. Here's my V2, here's my V1 as vectors, and delta V is equal to the final one minus the initial one. So when I'm doing a subtraction, I have the tails at the same location, I always end up at the one that is the first one in the subtraction. So this is what a picture of delta V would look like. It's going down and to the right like that. And of course, the average acceleration is just that scalar multiplied by 1 over delta t, but that just changes the length of it. So the average acceleration is in that direction. And these times are pretty close. So that's pretty close to the instantaneous acceleration. As you're rounding a curve, you're kind of accelerating in that direction. That agrees with the mnemonic that I gave you back in chapter 2, that acceleration corresponds to, or the direction of acceleration corresponds to the direction that your velocity is trending. So if I was going this way, and then my velocity turned out over there, it sort of trended in that direction, right? The same way. My velocity was going in this direction, and it ended up going in that direction. It trended towards that direction, if that means something to you. At least I think it's easier for me to remember that way. Okay. And similarly for the acceleration magnitude, that when we write something without a vector symbol, we mean the length of that vector, and if we know its components, that's the easiest way to find the length of the vector, is just use the Pythagorean theorem with the components. For those of you who did, I'm not going to do this in a worksheet, but for those of you who did watch the videos, you probably saw this was an example I used in the videos. But here's something where at one moment a radio controlled car has this velocity, at a later moment it has this velocity. What is its change in velocity vector? And similarly here, originally it had this velocity, then it changed exactly the opposite direction. What's its change in velocity vector, delta V? In this case, what I could do is I draw them with their tails at the same location. And if I want V2 minus V1, that ends up on V2 going between the two tips. So there's delta V in that location, in that case. Excuse me. And then over here, if I want V2 minus V1, I put the tails at the same location. So one tail was there. I'm going to put the other tail right there, pointing in the opposite direction. And V2 minus V1 goes from the V1 tip to the V2 tip. Okay, I'm just doing everything mechanically, not relying on intuition about velocities or anything like that. But so that's saying the average acceleration vector would be in the same direction as delta V. Okay. Let's do a couple of voting questions. So if you've got your voting cards, pull those out. If you don't, you can always, I do have a few extras, but I didn't bring them today. You can always do 1, 2, 3, 4 for A, B, C, D when you're voting, if for some reason you forgot it. Now this one, I actually, if you saw the videos, I'm not going to ask it to you because I put the solution up here because it's kind of a cheap and dirty shot. The answer was, this question makes no sense. And the point is, a rocket, so it's very tempting. Almost nobody chooses this, but I'm just going to explain this one. We will do 2 more voting questions in just a second. Rocket shoots straight up from Earth. Is its velocity vector positive or negative? Why wouldn't the answer make any sense? Or what might you be tempted to say there? What do you think the most common response is? Rockets shooting up from Earth. Is the velocity vector positive or negative? Yeah. Yeah. Positive. And why are you saying positive? What can you point to? It's going up, and up is always positive, right? Well, no. I mean, I could choose up to be positive y, or I could choose it to be positive x. Now, I don't have to choose my axes to be like this always relative to Earth. And in fact, if I'm out in deep space and there's just blackness everywhere, I'm floating in deep space, I mean, how would I judge which way is up, right? I don't really have a sense, right? If I say, hey, I'm going to shoot a bullet out in that direction, is that a positive velocity vector it has? We may like to have the velocity vector up relative to Earth, but there's no real axes on Earth. Now, even if you choose maybe you choose your axes. Here we are on Earth. We're gonna, rocket's gonna shoot straight up from the surface of Earth, and I choose my y-axis there. Giancolli would probably like that. He likes to make y upward. It still wouldn't make any sense to say a velocity vector like this. Here's a rocket going up. Its velocity vector is correctly drawn like that, but I wouldn't say it's positive. And for a technical reason, I would say its y component is positive and its x component is 0. And you can see there's a problem. I don't have to choose my axes horizontally and vertically, although you might be motivated in certain problems to do it. There are no real axes in the world. What if I chose my plus y axis to go in that direction, and I chose my plus x axis to go in that direction? I'm welcome to do that. It might make my analysis of this problem a little bit more difficult, but if you believed it was positive before, well, look, in going from tail to tip, am I not going more or less along the plus y direction, but I'm also going more or less along the negative x direction? So if I said it was positive or negative, there's no sense to it. What I should be saying is perhaps, vectors are not positive or negative. They point in a certain direction. If I put some axes there, I still wouldn't say the vector is positive or negative. I would say that its components are positive or negative. In this case, Vy would be positive. How would I think about that? Remember, to get the components, you go from the tail to the tip along the axis direction. So maybe first along the parallel to the x-axis till I'm just underneath it with respect to the y-axis, and then I go along the y direction. In going along the x direction, I'm going in the negative x direction. So that's a negative x component. In going along the y direction, I'm going in the positive y direction. So it would have a positive y component. The components are positive or negative. The vector itself isn't positive or negative. I know that's nitpicky. That's why I didn't actually have you vote on it here. Thought some of you might have watched the video and seen it given away. This one we're going to vote on. This is just trying to use the language of this, and things sound confusing, although if you think about them the right way, it's not confusing at all. So let's think about this one. For motion in 2D, so something's moving around in 2 dimensions, like that ant crawling around on the board, or a fly flying. Well, I guess flies don't usually fly in 2 dimensions, but is it possible for an object to change velocity without changing speed? So remember, we haven't been doing too many of these voting things, but when you figure out what your answer is going to be, you turn it to that. And then when we're ready to vote, you can hold it up. And you're not really supposed to be looking at everyone else's, but that way I get to see if there's a consensus in the room. Is it possible for something moving around on the board as time goes on to change its velocity without changing its speed? Okay, 2/3 of you are looking ready to vote. So if you got an answer, hold it up. It looks like the majority, it's not unanimous, but the majority is A, saying yes. Velocity is a vector, so it could change direction, or no, yes. In fact, I think I screwed this up. I put the answer on here. I colored it red. The problem was I had them all red, and then I switched them off. So it was supposed to just be yes or no. I forgot about that. But velocity is a vector, so it could change direction, right? When we say velocity, we mean something that has, by definition, a magnitude and a direction, whereas the speed is just the magnitude. Is it possible for something that has magnitude and direction to change without changing the magnitude? Sure. It could just, tilt over in different directions, but have the same length the whole time, right? So when I'm walking around in 2 dimensions here at a constant speed, I'm changing my velocity all the time, but I'm not changing my speed, or at least I'm imagining I'm not changing it, moving at 1 meter per second or something like that. Let's see if I gave the answer on the next one. Any questions on that one? I did put it on. The longer one is the answer because it has my explanation next to it. Sorry. So let's discuss then. For motion in 2D, is it possible for the velocity of an object to change without changing its acceleration? You know, you hear these and it's like, how do I disentangle this sentence? You got to think about the definitions, especially if you're not used to speaking this kind of language. Can the velocity of an object change without changing its acceleration? Boy, that's a real brain teaser. Until you think of it, you know, when something's accelerating, usually it is changing its velocity, right? When I drop this from rest, wouldn't everyone agree its velocity is changing? And we've already talked about free fall, that the acceleration is pretty much constant, right? And usually when you have constant acceleration, your velocity is changing, right? It means you're going faster and faster, or more generally, you could be changing your direction. But that's the usual case. It just sounds like something that might not be true, but it is possible for that to be the case. Any questions on that one? That was a screw up for me getting ready to do stuff that was done on the videos in class. Okay. I don't know how much I want to talk. I think I'm going to skip this example just for the expedience of time. You can, it's actually explained in the videos if you want to see it. Now let's go on to talk about what's at the end of, it's sort of the problem solving subject matter of chapter 3. And that is on projectile motion in 2 dimensions. So we're going to imagine taking something and tossing it through the air. Like in chapter 2, we were just talking about tossing things, you know, dropping things or tossing them straight up and down so they moved in 1 dimension. Now we're going to toss things so that they move genuinely in 2 dimensions along an arc through space. And 1-dimensional motion would be a sub case of this. Okay, so here's someone tossing a ball up in the air at t equals 0, maybe it's when it's just left the person's hand, and as time goes on, it goes up and it goes down. Is it clear that x and y are going to be some functions of t? They're going to be a function of time. X and y are going to change as time goes on. I've defined some x and y axes here, right? I chose plus y to be up and plus x to be sort of along the ground in the direction it's going. X and y will be some functions of time, and our goal here is to find those functions of time using what we already know about free fall. Okay. Since we've chosen plus y is up, you know, it's not too hard to believe that, you know, as you toss something through the air, it sort of goes at constant speed with respect to this direction, which is to say it's not accelerating along this direction as it's going up and going down. But it very definitely is going to accelerate along the direction toward Earth. We'll find out exactly why in the next chapter when we talk about the relationships between forces and acceleration. So if you like, think of it as when something, it's a generalization of the statement we made back in chapter 2. This object that is being thrown in that arc is in free fall the whole time. And when things are in free fall, they accelerate in the direction exactly toward the Earth. So the acceleration of the ball is always in the direction straight down. And that means if I take plus y to be up, ay would be minus 9.8. And if I take x to the side, a vector that points straight down has 0 x component, because in going from tail to tip, you don't have to move along the x direction at all. You do have to move along the negative y direction, or plus y, if you called this plus y, right? But you don't have to move along x. So the idea is these are the components of the acceleration vector, given that you've chosen y is in the positive direction up from Earth, and x is horizontal. It's not accelerating along the horizontal direction. Now, we can skip the same derivation that requires calculus that we skipped back in chapter 2, and that is under the assumption that ax was constant, we were able to show that these 3 kinematics equations followed from it. You get it by doing integrals if you're in a calculus-based physics course. Now we also know if the acceleration is 9.8 meters per second squared in that direction all the way through, ay is also constant all the way through this motion. And that means if I take an initial and a final that are somewhere in the period of time when the acceleration is constant, it follows from the fact that the y acceleration is constant that these these three equations follow, and they're the exact same equations. Notice that the only thing that's changed is the x has changed to a y. So everything in these equations has y subscripts. Everything in these equations has x subscripts. None of them are ever mixed. So one thing that you want to make sure that you never do is into one kinematics equation, put some x quantities and some y quantities, right? You wouldn't want to use the initial y velocity with the x acceleration. That doesn't appear in any equation. If you're putting one y thing in, it should be all y things. We'll do some practice with these in just a second. So what this is saying is that because all the x's appear together and all the y's appear together, how it moves along the y direction only depends on the initial y velocity and the subsequent y acceleration and the initial y position. And same thing with x. Sometimes, and Giancoli probably said something like this, sometimes that's referred to as the independence of horizontal and vertical motion. How things move vertically has nothing to do with how you shove them in the horizontal direction. They'll move in the vertical direction the same way. That's given by this picture. I'll do a demo in just a second. Here I'm going to imagine, here's a cannonball that's shot along an arc shown by, at different instants in time, those green dots right there, right? It's falling because it's under the influence of gravity. Now, if I imagine firing the same cannonball, but without the y acceleration, as time goes on, it would follow these blue dots, and it would be at exactly the same x locations because all I've changed is the y acceleration. I haven't changed the fact that the x acceleration is 0 because it's not being pulled in that direction. Similarly, if instead of exploding out and shooting it to the right, we just let it fall, it would have at each instant in time the same y coordinate as it did when it was shot over there, because the y acceleration is the same in those two cases between the yellow and the green. Okay, that's the idea of the independence of motion. It's also, here's another way of showing the same thing. If I roll a ball off the table at 3 different speeds, when it's rolling off the edge of the table, and we call that t equals 0, right when it leaves the edge of the table, the speed at which it's going when it leaves the table is sort of the initial x velocity, if I call that x. Maybe I call this plus y, right? Its initial x velocity is changing. That's not going to have any effect on its subsequent y motion. So you see with these 3 different initial speeds, at every time, it's at exactly the same y location as shown by those dots being at the same location. I brought a little demo that kind of shows, or at least you'll be able to hear. It's really old, as you can tell, and it doesn't like to move very much. But what I'm going to do is fire 2 little brass balls here in 2 different directions. So I've compressed a spring. When I flip this switch up, this thing is going to shoot over in that direction. It's going to knock one of these brass balls. Hopefully it doesn't hit anyone. It doesn't actually go that far. It'll probably end up there. So I tried to turn it so nobody was in the firing range. And each of these brass balls has a little hole through it, and there's a little protrusion on this side. I know some of you, it's right behind the machine. And what I'm going to do is put it on that part that's sticking out over there. Now, when I flip this up, the rod's going to move in that direction, and that's going to cease to support this ball, and it's just going to fall straight down. At the same exact time, it's going to smack into this ball because the spring is going to make it shoot in that direction and knock it in that direction. They'll both be released at the same time. One of them is just going to fall, and the other one's going to be shot out to the side, just like in this picture here, kind of. And we're going to listen with our ears to hear if they hit the ground at the same time. It's crucial that I have this completely level here, and at least I've got it eye level. So rather than, you can look if you can see, but listen with your ears for when the 2 hit the ground. That's showing, supposedly, that the horizontal motion that I gave this one did not affect how much time it takes to hit the ground. You hear the bounce going cluck, cluck, cluck. They both hit at exactly the same time on each bounce. So, okay, that's called the independence of motion. The lesson there is never mix your x's and your y's. Yes. We're going to do an example very shortly, which is almost exactly like this, and it kind of depends on what's being asked for and what you're given in the problem. Here, there were no numbers given, so it's hard to know what we know and what we want to know. In general, you'll want to use both, probably. So you're welcome to ask the question again after we do the first example on worksheet. Okay, now, so that was my demonstration. If gravity is the only significant force acting on the object while it's falling through the air resistance is negligible, then that's a case of constant acceleration. We mean a constant acceleration vector. It's 9.8 in that direction, which means if plus y is up, ay is minus 9.8. If x is horizontal, ax is 0, right? When an object is in contact with the cannon or my hand, right? If I'm in the process of pushing it up like this, my hand's exerting a force on the ball. I'm just appealing to your intuitive notion of force right now, since we haven't talked about it, right? So it's not a case of constant acceleration if I'm including a period of time when I'm actually pushing on the ball. It's got to be after it's released from my hand. That could be the initial time. And similarly, when the ball comes down and it hits the ground, well, the ground's exerting a significant upward force on the ball. And so you can't say, well, after it hits the ground and it's come to rest, that's going to be my final state in using these kinematics equations, because the ground, gravity is not the only significant force there. The ground is pushing up on it to keep it from burrowing into the ground. So I will often say when we're doing these problems, let's take the initial state to be just after it left my hand. As soon as it left contact with my hand, then gravity is the only significant force on it. And the final state is just before hitting the floor. Because sometimes people are tempted to say, oh, look, V final is 0 because it just hit the ground and it stopped. No, it's not 0. What we meant was V final should be the speed right before it hit the ground, or the velocity right before it hit the ground. Okay, let's look at some quick examples, and then we're going to do a worksheet, couple example problems. Same things as before. You've got to be careful about specifying what your axes, x and y, and where the origin is, which way the plus x and plus y is. You've got to specify what you're taking to be initial and final. We've seen this in examples in chapter 2 from the homework. Keep track of what you're given and keep track of what you want to know, and then grab the equation that's going to get you most directly there. But unlike what we saw in chapter 2, it's almost never a one and done. You're going to find you grab an equation that allows you to solve for the variable you want, and there's still another unknown variable in there. So you can, reduce it to, if I only knew t, then I could solve for x, which is what I want. And now I can go and look for something that will help me solve for t. Let's see an example of this. This was in the video, just so I'm not going to go through it in detail. So here's a major league pitcher throwing at 45 meters per second. We're imagining the ball is released exactly horizontally, probably not true for a pitcher. And of course, on the way to home plate, as it crosses over home plate, it's falling the whole way because gravity's pulling it down, right? It's accelerating downward. So it's released horizontally, but it doesn't keep flying horizontally. And the question is, how far does it go downward? How far does it drop on the way to home plate, which we're told is 18.4 meters away? Okay, we're given a lot of stuff. I've drawn a little cartoon here specifying this is where it's released from the pitcher's hand. This is supposed to be where home plate is. And I'm going to take my initial to be right after release and final to be just when it's passing, at the time when it's passing over home plate. Looking at those 6 kinematics equations, we might say, well, look, I know y initial is 0 in my coordinate system because I put it at the origin to begin with. What I'm after is y final. I want to know when it's passing over home plate, what is its y coordinate? And I'm expecting it to be negative, right? And of course, when I answer the question, I won't put the minus sign in there. When someone says, how far does it drop? I won't say minus 1.5 feet. That would be strange. You just tell them in normal language how far it dropped. But we're expecting a negative y final. So looking at this second kinematics equation here, I would say, that's going to allow me, this is my y final. I know y initial is 0. What's Vy initial here? If this is initial and this is final and these are my axes, what's Vy initial? It's 0 because it's moving horizontally. Its velocity vector initially is in that direction. Y is in that direction. In going from tail to tip, you don't have to move along Y at all. So its Y component is 0. It's not moving along the Y direction initially at all. So Y0 would be 0, Vy0 would be 0. I know AY in my coordinate system, AY would be minus 9.8, but unfortunately I don't know T. And so I say, if I only knew T, I'd be done because I could solve for that Y, which is what I want. And then I could say, well, I haven't used the 18.4 meters. Where could that come in? Well, that's an X distance that it traveled in between initial and final. So if I look at this equation, X final minus X initial is, X initial, I guess, is 0 here, but X final is 18.4. Vx initial is the 45 meters per second. Ax is what? 0, because X is horizontal and things only, when they're in free fall, they only accelerate vertically toward the Earth. So Ax is 0. That equation would allow me to solve for T, because I knew what was on this side. I knew everything except that T, and then I could plug it over there. That's a very typical kind of problem progression. Let me show you one more quick one, and then we'll do an example on a worksheet. Soccer ball is kicked from the ground at 22 meters per second, so its speed is up and to the right there. I'm sort of drawing roughly what its vector looks like there. At a speed of 22 meters per second, at angle 40 degrees above the horizontal. So this little angle in here, if you can see where my pointer is 40 degrees. How much later does it hit the level field and how far does it go? So how much time does it take to go up and down? And how far is it horizontally before it hits the ground relative to where it was kicked? You can see I've chosen horizontal and vertical, X and Y axes. Just for convenience, I chose the origin to be where it was kicked from, right? And it seems to make sense here to take just after the kick to be initial and just before hitting the ground to be final, right? Because those are things that have to do with what we're interested in. We're going to see in the kinematics equations, of course, Vx initial and Vy initial, the initial X and Y velocities appear in lots of places. The initial velocity was neither all along X or all along Y, but it was up at an angle of 40 degrees at 22 meters per second. And just for the sake of the video, let me stop sharing for a second, just to draw this a little bit bigger. 22 meters per second is the length of that initial velocity vector. So I'm drawing a picture of V initial, which has an X component and a Y component, right? Because I chose my X and Y to be roughly along those directions. So when I say I want Vx initial, what that means is here's a picture of V initial, this vector. Its X component is in going from tail to tip. How far do I go along X with the plus or minus sign? And then Vy initial is subsequently how far do I go along Y with the plus or minus sign? They'll both be positive here. I believe this was 40 degrees, is that correct? So going back to our trigonometry, remember I really like to pivot through the angle, and I really like cosine, or maybe you like SOHCAHTOA. So starting with 22, I multiply by the cosine of 40 degrees to get the X component, 22 cosine 40 degrees in meters per second. Whereas to get to this side over here, that's going to correspond to the initial Y velocity. I have to start at the hypotenuse and sweep across this angle. I'm not pivoting through it, but I'm sort of cutting across. I don't like doing that, and I don't like the sign for a completely illogical reason. But it helps me remember how to just write those down without having to solve for anything or think about what SOHCAHTOA means and translate it. It just, if you're doing that 10 times in a homework assignment, it just speeds things up quite a bit. All right, share screen back here. Okay, so we could calculate those numbers. I've just put those into my calculator. Make sure you're in degree mode in there. And then I wrote down all the things I know, and most importantly, the things I want. If this is my initial and this is my final, I want T, which is always the time between initial and final, and I want X final because I know X initial was 0, and so X final will tell me how far it went. These are the equations I have to choose from, the 6 of them, but there's really only 3. All that's changed is the X's and the Y's. So if I move this out of the way here. if I'm looking for x final, I might, say, well, it's got to be on the x side. That's one of the things I want. And I know everything on the other side of this x equation here on the left, except t. So I say to myself, if I only knew t, I could get x. Maybe I should have looked for t first, but I just didn't think to do it. I decided to go for x first. And it seems like, well, I better solve for t first, and then I can substitute it in here and get x. And I think about what I know about the y direction. Well, I know y initial is 0, y final is 0 in my coordinate system, right? So I know this is 0, this is 0. We just calculated vy initial. We know ay here. So the only unknown in this equation is t. Now, the t comes in with a square, but fortunately, we can get away without using the quadratic formula. So here's that y versus t equation. I've substituted in the 2 zeros and the vy initial. When you do that, if you ever have something that has the t squared term and the t term, but there's no constant term, you can always solve it by factoring and avoid that quadratic formula because you'll probably make a mistake with it. So here I said, look, there's a t factor in this term and a t factor in that term. I'm just going to factor it out in front of parentheses and then say when a product of two things equals 0, this is probably something somebody said over and over in high school, the first one equals 0 or the second one equals 0. Well, t equals 0 was when I kicked it. So that's not the one I'm looking for. It must be the other one. So I set this thing in parentheses equal to 0. And then once I found that, I substituted in the x equation, which is going to give me both answers there. Questions on that? We've got about 7 minutes left. Let's try just for like 4 minutes to start this first problem, and hopefully we'll have enough time to at least discuss it. If you wouldn't mind passing these straight back. 1, 2, 3. And we'll have to do another example, it looks like, on Monday, and then we'll be done with chapter 3. And you'll be giving me lots of other examples from the homework just because, so we can discuss those too. Even maybe one at the beginning of class if there's a really popular one. Okay, here, oh, sounds familiar. A ball is rolling off a horizontal table. That's like that cannon picture we sort of looked at before. Suddenly rolls, it should say off the edge and falls to the horizontal floor 1.6 meters below. Ignore air resistance. How much time does it take to reach the floor? And measured along the floor, how far does it go? So the first thing I would do is draw a little cartoon. And since we're pressed for time, I'm going to help you draw the cartoon. And then I'm going to let you puzzle over the kinematics that you could do with it. Cartoon might look like this. Here's the edge of the table. Here's the table leg. Here's the horizontal floor. We're told this distance is 1.6 meters, I guess, from the top of the table to the floor it's going to hit. Okay, let me unshare the screen so we'll get on the video. That's 1.6 meters. The ball, are we told its velocity here? 1.3 meters per second. So right when it leaves the edge of the table, it's traveling horizontally, of course, and its speed is 1.3 meters per second. And we all know its path is going to look sort of roughly like this. And so we want to know how much time it's in the air. And we want to know whatever this distance is from right below where it left the ground, where it left the edge of the table to where it lands or bounces the first time. All right, think about how you might approach those. And I would suggest that you choose some axes first and decide what's your initial and final going to be, because those decisions are important for using the kinematics equations. just so you have them up here at least. Well, maybe I'll share it too here. Let's share the screen just so you've got the kinematics equations in front of you. There they are, right, come on. There they are at the bottom. It's the same ones you've been using. They're just duplicated for X and Y. So there's not a whole lot more to really commit to memory. But sometimes it helps to have them written out in front of you so you can sort of look at what you want to know, decide what equations might help you find that. Okay, which one did I ask for first? T? How much time does it take to reach the floor? Unfortunate thing about T is that it appears in 4 of the 6 equations, so that's not helping me narrow it down at all. And I'm going to have to think about what information I'm given. I'm really given 2 things, and I also know the acceleration X and Y, but I haven't picked my axes and origin. Doesn't really matter so much, but I'm just going to make a definite decision and maybe put my origin down on the floor right below where the ball leaves the table, and I'm going to call plus Y up and plus X along the floor direction that it's moving. You could have done it up here. That would have been just as good. Sort of nice to do it in either one of those places. And I'm going to call, of course, there's not too much choice here. This is my initial right after it rolls off the table, and this is my final, I mean just before it hits the floor. And what do I know? Well, I know a 1.6 meters. That has to do with the Y direction, right? The height it falls through. 1.6 meters, well, I would say in this case, Y initial is 1.6 meters and Y final is 0 in my coordinate system, right? So I know my Y initial and Y final. That means that I might be able to use this particular equation right here, right? I know my Y final, I know my Y initial. What's my Vy initial?
0.
0. Someone came in from out of the void, and that's good. It's 0 because initially it's moving in the horizontal direction, and Y is vertical here. So the Y component is 0 of the initial velocity, right? It's moving horizontally as it rolls off the table. So let's write down that equation, then let's plug some stuff in. Y equals Y0 plus Vy0 t plus 1/2 AY t squared. In my coordinate system, Y final is 0. Y initial is 1.6. I'm suppressing the units because we have everything in SI units. Vy initial is 0. So I don't really care about the t there. I'm hoping I get a t from this one because that's what I want to solve for. What's AY in my coordinate system? Negative 9.8 because I chose plus Y up. Doesn't matter if you chose it down, you just need to be consistent. So this is minus 9.8 times t squared. Yes, technically it's a quadratic equation, but all you got to do is square root both sides, right? So what I do is say, put this over here with a minus sign, multiply by 2, divided by minus 9.8. That would give me t squared is minus 1.6 times 2 divided by 9.8. And I could do that in my calculator and then take the square root of it. And you'll get, according to my notes here, t equals 0.571 seconds, a little over half a second it's in the air. And I see we're over time now, but let me just finish up by asking, now I want X final. Now that I've got T, do we have a leading candidate here? There are 2 equations that have X finals in them. Unfortunately, well, This one's not going to help so much. Why? I want to solve for x final. That's the part B. What's wrong with it? Ax is 0. It's not accelerating along that direction. So the thing I want is being multiplied by 0. So this is your only hope here. X0, I'm sorry, I'm drawing somewhere where the folks at home can't see. X0 is 0. Vx0 is given, so we know that. We now know the t in between initial and final, and we know ax is 0. So this term's going to go to 0 also, right? Because ax is 0. So all I've got to do is multiply the Vx initial that we were given in the problem with the time that we just calculated in part A, and that would allow me to solve for x final. Okay, wow, blazing speed, but I want you to hold on to this worksheet. We're going to do at least the next problem on Monday on this worksheet. And in fact, I will probably post the solutions to this worksheet prematurely because I know some of you will want to work on the homework over the weekend, and it might help you to just sort of look through what the solutions look like, even though we can go through at least one of those two problems on Monday. And then hopefully on Monday, we're going to be back to our normal speed. All right. If you're hanging out to ask questions, that's fine. Otherwise, have a wonderful weekend. And let's hope that it warms up as much as it's supposed to, and there's no snow on Monday on campus.